Yeah, cool. So what is that showing you here? Let's say the voltage was 10 volts. Let's say the resistor was 2 kilo ohms. Let's say the capacitor was 5 millifarads. I'm going to make the numbers sort of easy to work. Okay, so then what's going to be the charge? So this tells us how the charge of the capacitor will change as a function of time, right? So then Q of T is going to be C is going to be the 5 millifarads. And then VB is going to be the 10. And then, so you have here, that's going to be 50 millifarads. And then you're going to have parentheses, 1 minus e to the minus t over, and then the RC is going to be the product of the capacitor and the resistor. So I did it kind of to make it easy. The milli and the kilo is going to cancel when I take the product, and it's just going to get 2 times 5, which is 10. Okay, so we could kind of plot that on Desmos. Back to our trustworthy Desmos, right? So Q equals, so the 50 millifarads can be written as 0.05, 1 minus e to the power negative t over 10. So let's zoom out. Oh, it's so small because this is 0.05. Why don't we just graph it as a millifarad on the vertical axis instead of farads? So I'll just keep it as 50. Okay, then that'll be better. So just know that the vertical we're graphing as a millifarad. Okay, so what is that showing? This is showing you how the charge on the capacitor asymptotically builds up to its maximum value. And its maximum value is the 50 millifarads. No, sorry. That should be 50 millicoulombs. Hold on. Yeah, when you multiply C times CVB, I'm multiplying 5 millifarads times 10 volts. Volts times farads is coulombs. So remember, C is equal to QV, Q is equal to CV. So this thing here, CVB, should have units of coulombs. So this is 50 millicoulombs. Okay, so the vertical axis here, the vertical axis is in millicoulombs. So the maximum charge of the capacitor will be 50 millicoulombs. Okay. And then what does this 10 represent? What does this 10 represent? Anyone know what's that called? This RC. Today's lab is on that. What is that called? It's called the time constant. The time constant of the RC circuit. Time constant. Time constant. So tau, symbol is tau. RC. So when you multiply resistance times capacitance, you get units of time. So in our case, the time constant is 10 seconds. 10 seconds when you multiply 2 times 5. So essentially, it's an indication of the speed at which this capacitor is charging, the speed at which it's charging in that circuit. The bigger the capacitor, the longer it will take it to charge, right? So if this increases, then the time constant will also increase. If the resistance increases, the time constant will also increase. So in one time constant, what's going to happen? In t is equal to 1 time constant, q as a function of t, 1 minus e to the minus, when t is equal to 10, you're just going to get 1 here, right? So when t is equal to 10, you're just going to get 1. And within one time constant, this will always be true. The charge will build up to what? 1 minus e to the power, hold on. Let's do e to the power 1 negative minus 1. Okay, yeah, so this thing comes out to be 0.632. So within one time constant, the charge will build up to 63% of its maximum value. So this thing comes out to be 63.2%. So that's a characteristic time for an RC circuit. The bigger the resistance, the bigger the capacitance, it takes longer to charge. So if the resistance is large, that limits the amount of current that that circuit can take. So if the resistance is large, it should take it longer to charge, right? And then if the capacitor is big, that increases its potential to be charged, right? It can take more charge. And so that should also make it charge. It should take longer. So if we look at the graph here, right? So during in 10 seconds, if you go up here, I wish I could draw a line here. If you go up, oh, it doesn't let you. So if you draw a line, okay, there's 10 seconds, right? And 10 seconds, what's the charge of the capacitor? 31.606 millicoulombs. What's the eventual charge of the capacitor? Well, it's building up to 50 millicoulombs. So if you divide the charge at 10 seconds, what do you get? What is the charge at 10 seconds? 31.606, right? So if you divide the charge at 10 seconds is 31.606. The final charge at infinity is approaching 50. When you take that ratio, you should get 63.2%. Yep, 63.632. So that's always true with any capacitor circuit. So we could graph a bunch of these and say, what happens if I just keep the capacitance the same and just change the resistance? let's see here. Copy, paste, paste, paste. Okay, so let's say I changed it. What was my resistance? 2 kilo ohms, right? Let's say I change it to 3 kilo ohms. The resistance to 3. Then what will change here in the equation? If I change the resistance here, nothing changes here. Just this one goes up 3. This one goes up to 3 times 5. That's going to be 15. You see? So if I keep the capacitance the same, change the resistance, we would expect it to so then this one should be 15. Okay. Then if I change it to 4 kilo ohms, this one should change to 20. If I change to 5 kilo ohms, this one should change to 25. So how does the RC circuit charging change if I keep the voltage of the battery the same, the capacitance the same, but just increase the resistance of the circuit? You see? So this is the highest resistance. What has happened here? You see, the red one is the lowest resistance. So the less resistance, it charges quicker. Its time constant is less, right? So it takes 10 seconds to reach 63%. This guy takes how many seconds? It takes 15 seconds to reach 63%. You see? Because the time constant is 15. And then this guy takes 20 seconds to reach 63% of its maximum. But the maximum I haven't changed, you see? And then this guy takes 25 seconds. You see what's happening? So the bigger the resistance, it's kind of, this one is more like this. It takes longer for it to charge, you see? Now, what if I keep the resistance the same, but change the capacitance? What happens then? Let's say I go from 5 capacitance to 6 to 7, like that. Now, how does the equation change? So that's how you can kind of graphically study. So now I keep this at 2. Now I change this to 6, 7, 8. So then what happens? Well, the capacitance affects two things, this guy and this guy, right? So if I increase it, this will also increase, you see? So then if I change the capacitance to 6, what's going to happen? This is going to increase to 60. And this is going to increase to what? If I increase to 6, it's going to be 6 times 2, 12. Oop. Now, if I change to 7, 70. 7 times 2, 14. If I change to 8, 80. 8 times 2 is 16. Okay, now how do you compare them? Are their time constants the same? No. It's taking longer to charge, but they're also reaching a higher charge, right? This guy is reaching a higher charge. So how would you describe that? Let's see. If you increase the capacitance, it reaches a higher charge, right? And it also takes it a longer time to reach that higher charge, you see? So why is that doing that? oops. So for this guy, what is the time constant of this guy? 16. So 16 is 12. You see, this guy is now 60%, 63% charged. But for the green one, it takes 14 seconds. So now this guy is, oops. Now this guy is charged, you see. So the time constants are like also increasing, but the maximums are also increasing. So yeah, it kind of makes sense. So you can kind of see graphical interpretation is always very, very helpful. Now, once you derive the equation for the charge in the circuit, what else can you do? Okay, so we've got the equation for the charge right here. Well, once we know the charge, we can then remember voltage of capacitor is charge over C. So once you know the charge of the capacitor, just divide this by C and you'll have an equation for the voltage of the capacitor, the voltage across the capacitor. So then just get rid of the C and then VB 1 minus e to the minus T over RC. So it's pretty much the same equation, except it doesn't have the C. So now we know how the voltage of the charge, how the charge is going to behave. It's going to increase, and the voltage of the capacitor is going to exponentially increase, right? And then, okay, now how about the current in the circuit? Remember earlier, we had predicted that the current opposite should happen. Well, initial current should be very large because the capacitor is not opposing you. And then the current should start dropping as the capacitor starts to behave like an opposite battery. So the current should start dropping. So how can I derive the current equation? Well, once you have the charge, the current is the derivative of the charge. So that's it. I don't have to do another differential equation for that, right? I can say I is equal to dq dt, right? Then take the derivative of this guy. What happens when you take the derivative? CVB, and then you take the derivative of this guy. So it's just itself, and then the negative 1 over RC comes out. So then you'll get, let's see here, negative 1 over RC, e to the minus T over RC. But the derivative of 1 is 0, so that disappears. So you get this like this. So it looks like this. And then the C cancels the C, and then the negatives cancel. dB over R, e to the minus T over RC. Okay, so the current behaves like that. And now what's going to be the voltage of the voltage across the resistor? Voltage across the resistor is IR. So then just simply multiply this by R, and then that you get rid of that, the R. So the voltage of let's see how that kind of function behaves with the same numbers. So let's say it's 2 kilo ohm. What was my original value? 5 millifarads. So what's the current going to look like? 10 volts over R, 2 kilo ohms, times e to the minus T over, and then 10 again. So then this one I could write as what? 5, and then 1 over kilo is milli. 5 milliamps. So 5 milliamps e to the minus t over 10. Right, and then now we could graph that. So you get rid of basically the 1 minus, and you just have, so then you have 5 milliamps. Yep, that's what it looks like. Oops. Why? See how it's a decreasing function, the current? So then we can say, well, what happens if I keep the resistance the same again, but only change the capacitance? And then what happens if I keep the capacitance the same, only change the resistance? So let's do the first one. Keep the capacitance at 5, and then change the resistance to 3, 4, 5, like that. So if I keep the capacitance at 5, change the resistance to 3, kind of the same order that, so I'm going to keep this at 5. I'm going to make this 2, 3, 4, 5. So then what happens? This becomes 2, 3, 4, 5. This number also goes up, right? So you basically have 10 over 3, 10 over 4, 10 over 5. And then this one also goes up. So then what happens here? This becomes 10 over 3 is 10.333. And then if I change it to 3, that's going to be 15. Then if I change that to 4, 10 over 4 is going to be 2.5. Four times 5 is going to be 20. So this is like the first scenario that I did. And then this one is going to be 10 over 5, so it's going to be 2. $25. So how do you compare those now? Let's see. This one is the red one. So this is the least keeps doing that. This is the least resistance. This is the least resistance, so it's got the highest current. And their time constants are different too, right? Yeah. They're all eventually, it looks like they crisscross. Oh, okay, hold on. Let's see here. Why do they crisscross? I don't think did the other ones crisscross? I don't think so. This one goes like this. It drops faster. See here, the current starts high, but drops faster for this guy. Oh, because the time constant is the least. So this is the least resistance, right? Oh, if it's least resistance, then the time constant is shorter, right? It's only 10 seconds here. 10 seconds is the time constant. So that means if its time constant is shorter, that means it should start decreasing quicker, you see? So it starts out higher, that's why it crisscrosses, and then its current decreases much, much quicker, you see? Whereas this one, if it's 3 ohms, it starts out less current, but it maintains its current longer. And then the highest resistance starts out the least current, but it maintains longer because its time constant is the longest. So then in one time constant, how much should the current drop? To what value should it drop? We can ask that. In one time constant, in t is equal to tau, then we're going to have the current is going to be VB over R e to the minus 1. So what's that ratio? E to the minus 1. It's 0.367. In other words, it's the missing piece. The other one was 0.632. This is 0.367. When you add them, you get 1. So in the charge of the capacitor in one time constant builds up to 63% of its value, but the current in the circuit drops to 37% of its value. You see, 36.7%, so about 37. And when you add 37 to 63, you get 100. So what's happening here then, the time constant of this red one is 10 seconds. What is the current at that point? 1.839, right? So if I take that value, 1.839, that's milliamps. And then if I divide by the original current, what was it? 5 amps, what should that ratio be? You see? What should that ratio be? Well, if this is true, it should be 36.7%, right? So in one time constant, the current should decay to to 36% of its value. 1.839. There you go. Nice. Nice, nice, nice. Okay. Let's see. And of course, we could say, let's keep the resistance the same, change the capacitance, but that's only going to change this guy, right? The same similar thing is going to happen with the charge of the capacitor. Changing the capacitance changed how the final charge it reaches. For this guy, changing the capacitor isn't going to change anything except the RC constant, you see. Okay, so now some of the other equations that I have on the review sheet. Test reviews. See, this is the charge equation, the charging, and then this is the current equation. You see, this is the two equations that I just proved right here, the charge and the current.